in her recording soon. Yeah, thanks. Okay, maybe we should get ready to start. It's 2 past 1 p.m. here. All right. Good afternoon or good morning, everyone. Thank you for joining our AFMS seminar series. And for this month, we are lucky to have Professor Sarah Wicks to give us a talk. Sarah is an applied mathematician and engineer based at the University of Otago. She's been the head of Department of Mathematics and Statistics as well. And today we will be having a talk on her research work on CFD data and the field. Floor is yours, Sarah.
Thank you very much, Morgan. Kia ora koutou, ko Sarah Wakes toku ingoa. Thank you very much for inviting me. I'm sorry this is was postponed from last year. I was really sick on the day I was meant to be presenting. And apologies to anyone who's seen parts of this. Some people might have done. So I thought I'd talk to you today about one of the main areas that I do research in. It's not the only area, but it's something that's been I've done really since my PhD. I had a break and then I picked it up again at the University of Otago. So it's really looking at wind flow modeling over dune systems, complex coastal dune systems. I've been looking at for the past 24 years that I've been at Otago. I'm going to talk to you today about sort of some of the work that myself and some of my PhD students and postdocs have done in this area. And I'm particularly interested in how we use sort of CFD modeling and fieldwork to sort of advance our understanding of these sort of complex flow situations. So the focus, if I can get through it all in time, and please stop me if I go over time, I'm going to be looking at some work I've done, or I'm still doing really, on surface roughness of a dune from vegetation, looking at sort of how and what to measure and how being in the field can really help us understand what's important in modelling, talk about some conceptual and parametric model development, uses and predictions, and then some work we did on machine learning and CFD in this sort of space. Okay. So dune systems, particularly coastal dune systems, come in lots of different shapes and sizes. I'm sure we can all visualize them. We've hopefully all been to the beach and we've all been to beaches that have dunes on them. They're really complex systems. We can see in the middle picture, they can be really large scale structures. That middle picture is Rakiura Stewart Island on the west coast. And that's a dune system that myself and my collaborators have done quite a lot of work around. We have moving sand. We see top left, some saltating sand, so that's sand being picked up by the wind. We have dunes that have vegetation cover of varying degrees of types of vegetation and density. We have variable wind speed and directions, and we have sometimes very dynamic dune morphology. So the morphology can really be changing quite rapidly, but also quite slowly, so different time scales. So we can see that the physical context is really challenging for us, and particularly for sort of modeling and going out and doing measurements. So in the sort of physical context, some of the big questions that geomorphologists are trying to answer are things like, what's the interaction between dune form, wind flow, sediment transport, and vegetation on the dunes? So, as you can see, that's got a big overarching question. Can we develop conceptual models for dune development that are applicable across these dynamic landscapes? And can we use this knowledge to develop mitigation and adaptation plans for dune systems to protect our coastline? And the picture on the right is a sort of example really of a conceptual model that comes out of that coastal geomorphology. So not from a modeling perspective, from more a sort of measurement out in the field perspective. And this one particularly is trying to understand and develop and give us a model for how wind direction and sediment transport respond across different beach dune systems. So some of the fluid dynamic work we've been doing, as I say, I've been doing, I did my PhD on looking at dune systems, but they were desert dune systems. But then I picked the work back up when I came to Otago, and we've really sort of developed our understanding, but also our ability to what we can do. We started doing relatively straightforward, well, not straightforward, relatively simple two-dimensional models, and we've built up so that we can use LiDAR data to really model some quite reasonably large, complex dune systems. We see the sort of meshed surface there on the right. That's from Rakiura Stewart Island, one of the parabolic dunes on Mason Bay, and we can see different ways in which we can mesh it, smooth out some of the lumps and bumps we get from that LiDAR data. We've also used dunes closer to hand. So the pictures in the middle and on the left are in Dunedin, which is where I'm based on the east coast of New Zealand, the South Island. And this is where we have a sort of relatively artificial dune with we can see John Wilson Drive above it. So quite a constrained, non-dynamic dune. And my PhD student, or he's done his PhD now, he did a lot of work, and we looked at some artificial ways of taking sand and mitigating some of the storm damage that you can sometimes get on these dune systems, especially when you have a not moving dune system, undynamic dune system. So I will say I'm not an experimentalist. I don't really go out in the field, but I will explain to you why it's important. And this is part of the reason why I do modeling, is that it can be quite a challenging environment. Here we've got moving sand, we've got really high winds, we've got rain, and these poor guys, none of which are me, thank goodness I wasn't there. They have to go out and they have to try and put masts up, they have to try and measure wind, they have to try and measure and gather sort of sediment that's being transported. They have to make sure the data loggers are dry, all that sort of stuff. So, hats off to them. It's a really challenging thing to do, but the work I do, it is crucial that we have that data and that we understand what's going on in the field before we try and model it. So yeah, that's why I do modeling. But I'll go into my sort of first sort of little subsection here. The picture on right, you can see one of those people is me. We're flying. Well, I'm not flying. My colleague Teresa is flying the drone. And actually, those of you who are in Australia, you may recognise that beach. That is Summerlands Beach on Phillip Island. It's where the penguins come in. And we were lucky enough to get permission to do some modelling. The penguins are the other end of the beach. We're not disturbing them. It was part of some work we did on looking at vegetation roughness. And I'm going to talk here about how that field data is really important for sort of model creation in terms of this surface roughness. So I've been interested sort of since I picked back up my dune work about how the vegetation on coastal dunes affects the wind flow. And, we don't really, it's not really been accounted for in a lot of CFD models. In fact, the paper we wrote in 2010, I think, was the first time that anybody had attempted to put a roughness on a surface of a CFD model of a dune. So I wanted something that was a little bit more real life. And what we see when we're out in the field, and again, this is the first lesson, going out in the field, this is what you see. You see that the vegetation on a dune, it moves with the wind. And that maybe not be a revelation, but also that what that means is that as that vegetation lodges or bends over, the smoothness or the roughness changes as the wind changes. And so that is a really dynamic element to our modelling that we don't include. And that could have some significance, particularly for sediment transportation and sediment accretion and erosion on those dune systems, because that vegetation is really important for that. So I wanted to build a dynamic vegetation model to better reflect this sort of lodging of vegetation and change in roughness. And we can see here, this is marron grass, and we can see that in wind it bends over. And this actually was we were doing field work on Stewart Island, and sort of one of the revelations I had, and this is why it's important modelers go into the field, I think, is that we were on quite a steep dune slope, and I realised that the vegetation didn't grow out perpendicular to the dune surface. It actually was already bent, and it already grew in the direction of the prevalent wind direction. And that was really important from when we got our wind data, and I could see a model or a pattern emerging, and I could understand it because I'd seen what had happened in the field. So really important. So what we did is we measured wind data and we derived a surface roughness from that. Took lots and lots of measurements over a period of time, and I tried to develop a very simple model, just fitting plotting our roughness against our average incident wind. That's our wind at sort of 5 or 6 meters above the dune surface, to see if there was a pattern. Now, my proviso here is that we had limited data whenever we go into the field. We're very reliant on the wind blowing, our instruments working, and actually getting sort of useful data. And we had some useful data, but it was in quite a narrow range of wind speeds. And so we've developed a model based on what we get. It's not the best model in the world, but it was enough that I could start trying to use that with my CFD software. So this was actually a lockdown sort of project. It was useful being at home. We had this model derived from field data, and I finally got it, wrote a user subroutine. I use ANSYS Fluent, and I connected that, not an easy task, to my Fluent, and we finally got it working, that we could have this dynamic roughness. Every iteration, we would test the velocity 5 meters above the dune surface. It would use our model, change the roughness on the surface, do the next iteration, and keep going. And this picture is just showing the roughness, the dune surface, and how the roughness is changing on the Stoss slope. So that's that steep slope at the left, across the crest, and as we go into the lee of the dune. So that was like quite a major achievement, actually, just to get that working. What we see, this was one of our anemometers on one of the slopes, and we can see how the marron grass bends over in the prevalent wind direction. And we're often limited. We're often just, this was 3 instruments on our mast. We often have 3 or 5. So we're really limited in the sort of wind profile that we can measure in the field. These instruments are not cheap. This was actually our model on that slope. So what we found for marron grass on these really tall dunes is that we have different behavior on the crest of the dune and on the Stoss slope. That's the slope facing the sort of beach, with the prevalent wind coming in. And we can see here that what happens here is that as the wind blows harder, we get this sort of relatively linear model. We can fit a pretty decent linear model, so that what that means is the surface is getting smoother as our wind is blowing harder. What we find with the crest is that it's more of that quadratic model, i.e. we're getting a peak of roughness, and we're getting something that looks a bit more like a wheat field sort of blowing in the wind. So important that we'd done those measurements, we'd thought about what's happening, and we'd witnessed what's happened in the field. But the important thing is, does it make any difference to our simulations? If we simulate now our flow over, in this case, we put it over a low ideal, sort of bit of a simplified dune. And what does that give us? Well, this is going from beach. So this is on the beach. We're seeing no difference because we've got no difference in our roughness. As we get to the toe of the dune, again, we're not seeing anything different. It's not really encountered the vegetation, this changing dynamic roughness model. Um, but as we go up the slope, we're starting to see some difference. So our vertical axis is height above the surface, and then our normalized velocity is the x-axis. Um, and we can see I'm using various models here, but we can see the yellow is the sand, just a sand roughness. Light green is a constant roughness for the vegetation. And then we can see the darkest green is this dynamic model. We'll just ignore the other ones. And we can see that there's a real difference in that peak of velocity around sort of 1 to 2 meters. And as we keep going over the crest, to the back of the crest, into the lee where we're getting recirculation behind our dune, we can really see the difference there in that sort of, you know, surface to sort of 2.5, 3 meters above the dune. And that's where the sediment transport, the erosion accretion is happening. So we know that this is making a difference. So we possibly need to include a better roughness model in our CFD models. And we continue our lee toe into our deflation zone. So that's the part behind the dune. And we can also do, this is a line along the center. And again, it's just showing that once we get sort of to that crest, we're seeing quite a big difference between our models. And this is 10 centimeters above the surface, 50 centimeters, and 1 meter. So we're still getting those effects, you know, pretty high above the dune surface. It also affects flow deflection. So as flow comes in, it deflects sometimes up the stoss face, and that can be important if you're trying to direct the wind, or if you're moving sediment or sediment is moving across the dune. And so I won't explain this in great detail because I don't really have time, but what we see is that a changing roughness, a dynamic roughness, gives us a different deflection pattern or different deflection angles than a constant roughness or a sand roughness. So we were pretty pleased with these results that it shows, and sort of ongoing work now is actually putting these onto real topologies of dunes, and both low, Summerlands were very low dunes, and onto our Stewart Island, which were quite tall, 6 to 10 meter high dunes. So ongoing work. This is some I've done over a taller simplified dune. This shows us our roughness, and I've also put it over a real dune. We can see those in the dashed lines. And we can see again that we're seeing differences behind the dune. So in that area where we're getting sediment accretion and erosion. Okay, so a little bit of work also I wanted to talk about, and this, well, it does involve going out in the field, but sort of a few years ago, we wanted to measure how much sediment was being transported. And there are various ways of doing that are documented in the literature. But my colleague, Mike Houghton in geography, had this idea that we could do this more effectively. And the idea was to have, instead of a static collector for sediment, that we would have a dynamic collector that actually moved with the wind, because wind doesn't just blow in one direction like it does in a CFD model. It changes direction and is gusty, and there's lots going on with it. And you have to sort of guess when you put these sediment traps in what direction the wind's going to be blowing in so that you get most of the sediment that's being transported. This was quite an ingenious idea between him and our technician, Bill, to actually have a moving catcher. And they built it, as you'll see in the next slide, out of some plumbing pipe and a rod. And then our PhD student, Duck, at the time, made those little mesh bags on my sewing machine. So it was a real DIY job, but we wanted to make sure that it was doing at least as good a job as the current traps, And actually, we wanted to show that it did a better job, that it was effective and efficient, and that we were aware of what the measurement errors were. So we did some wind tunnel testing up in Canterbury. Mark Germany helped us with that. We did work out in the field, and I did some CFD modeling looking at different scenarios of these traps in different arrays. So basically, you don't just put one in, you put arrays of, sort of in line and also multiple ones on a post. And we wanted to see if they were interfering with each other, if we had arrays behind each other, how that affected the wind flow. We didn't model the sediment, we just modeled the airflow into them. And all of that was published in this paper. And this was just some of the work. We wanted to see the effect of the pole versus not the pole, modeling it. And what we found was, having seen how these behave in the wind tunnel in the field, is there is this lag, so they don't move immediately, and especially when they've got sediment, often which is wet, so it's quite heavy. There is this sort of time lag, and we showed that this sort of lag of about 15 degrees doesn't make that much difference to the wind flowing into these, the air flowing into these traps, and hence we assume the sediment being carried by the wind into these traps. So that was a really nice bit of work where CFD could really help understand and develop an instrument that makes catching and trapping sediment a little bit easier, and take some of the guesswork out of what we do there. Okay. So I'll just very briefly go over some of the work that we've done on John Wilson Drive in Dunedin, in Ocean Beach. So this was around these notches that, with the council's permission, were cut into the dune system. And we were really interested in how those notches, and they were all of differing geometries and slopes and sizes, how effective they were at moving sand sort of from the beach to the back dune, into that sort of little gully between the steep slope up to the road. And this was all about mitigation and adaptation. So that John Wilson Drive and that artificial dune sort of creates a big hard surface that, when we have storms, can get eroded quite quickly, and is actually built up from some very old landfill. And so the council, nobody wants that exposed. So we need to find ways in which we can do a little bit of protection, take some momentum out of those big sort of storm events. And this is one idea that the council very nicely allowed us to do. And so Dirk, our PhD student, did quite a bit of work looking at various simulations and field work, looking at how sediment and airflow moved through these notches in a variety of different ways. So this, for example, this paper, he looked at how sand was being deposited behind the fore-dune in this gully, and how that matched up with the sort of CFD work that he undertook. So that was a really nice study that he did. He also then went on to look at some conceptual model creation. So can we, from this work, develop some ideas of how we might be able to use these notches in another situation? So are there some rules that we can develop that explain what's going on? So he looked at different orientations of the wind coming in, see how the airflow behaved through these little notches or gullies, and what happened behind the dune. And he came up with this sort of conceptual model about whether the notch was inactive, i.e. it didn't really transport very much air through and not much sediment. Consequently, whether we have two types, and then there was two types of notch activation, where in the first one we had flow compression and acceleration, the other one we had flow separation and deceleration, and those are important for erosion and accretion of sediment in your dune system and where they're being deposited or not. So I think that was a really nice way that field data CFD sort of came together to try and create a conceptual model that tried to explain how these notches were working. So he's taken that one step further and built a sort of what we call a parametric model. So this is where we sort of take some of the ideas and simplify the geometry. We did this, I think this is, as we can see, a very simple three-dimensional model of a dune system, but with the idea that we're changing some of the key parameters. So the width of the slot, the depth of the slot, those sorts of things. So can we actually parameterize it and understand how changing some of those things, including the slope of the notch as it goes towards the back dune? And here are some of the results. We can see this is we can see the flow changing at the edges of the notch. We're sort of looking into the notches here. We can see how the walls of the notch, depending on what angle they're at, how that affects the flow through the notch, and how the width of the notch affects the flow that we get through. And looking and seeing when we have flow coming in at an angle, which is often the case, again, we can't predict often what wind direction they're coming in, except in a very general form. So if we're getting things in perpendicular at the top and then at a 20-degree oblique angle, 40 and 60, how that affects what's happening in the notch. So where we're getting low flow, where we might be getting accretion of sediment, and where we get high flow, where we might be getting erosion of the walls and sediment being released, sand being released. So again, that brought us to sort of a conceptual model, and that was these sort of very parametric notches or blowouts, as they might be called, and what leads to a sort of stable blowout or something that is a bit more dynamic in terms of shape factors and in terms of our incident wind factors. And we can see that they are sort of related in that. He then also looked at future possibilities. So what are some of the things that could be done? I mean, these are sort of theoretical. They're probably unlikely to ever be done because it would be way too expensive. But what are some of those things that could be done in this situation and what effect would they have? So basically, another sort of taking a two-dimensional model sort of through the dune and John Wilson Drive and seeing what happens if we move John Wilson Drive back, or if we move the slope of the dune that goes up towards that road, and what would happen to the flow. And so this, for example, is moving John Wilson Drive back or moving the dune forward, the fore dune forward, although there's not a lot of room to do that, and just seeing what's happening with the flow. So where we would get, our areas of low flow or recirculation, and we get deposition of sand, where we might get high sort of erosion, where we're getting our speed up at the top of John Wilson Drive, that little sort of jet of air is that's quite a known phenomenon with dunes, that we get a speed up our stoss faces, ones that face the wind. Yeah, and these are distances, and looking at this parametric model. Please read the paper if you want to know more. I'm really just skirting over some of these. Also looking at what goes on, where the recirculation areas are, if we move John Wilson Drive back, and the effect that might have, and what happens with the different slopes. So if we adjust that slope from a sort of 90-degree, very vertical cliff-like wall back to something that's much more gentle, and how that affects the flow. and we get these different recirculation patterns between the dune and John Wilson Drive. And it just sort of will help. These are all future possibilities that might help the council in terms of how they deal with this dune system, because it is problematic, and it does cost them money. We have, it used to be a highly dynamic dune system. They then sort of reclaimed the land behind it and then built John Wilson Drive on this old landfill to sort of try and stabilize everything, but it's actually created quite a lot of problems on the beach. So the final thing I wanted to talk about is some work we did using CFD and machine learning in this sort of dune space. So with my colleague Bernie Bauer in Canada, we were interested in what causes sort of recirculation areas behind the dune, but particularly in front of dunes. And we knew that these only occurred sort of in very particular situations. But when you're out in the field, every dune system is sort of unique, and they're not the nice, neat geometries that we get, in CFD. So we wanted to try and pinpoint what important variables in the flow and the geometry of the dune might be influencing some of these flow structures. So we wanted, and we thought that with a colleague, Mike Mayo up at Waikato, we thought machine learning might be the way in which we could do this. So we wanted to identify patterns. We identified a number of variables that we thought might have an effect. And it just was not possible to do either field or lab experiments or do all the CFD experiments that we wanted to do in order to try and determine what the effects were. So what we did was we took a very simplified two-dimensional simulation form of the dune, and we had 5 things in this dune that we varied. So we varied the dune height, we varied the width of the crest, we varied the Stoss angle and the Lee angle, and the sort of how rounded the crest, the sort of Stoss to crest and Lee to crest dune bit was. So those were our dune parameters. And then we also varied velocity and angular velocity, obliqueness of our flow. And we can see in the table, these were, again, published in the Royal Society of New Zealand Journal. We can see the parameters. So we had 3 wind speeds, for example. We had 5 wind angles. I can't even remember. We had, I think, 5 dune heights, for example. So we had a lot of different variables, and it would have meant, I think, around, I don't know, 600 odd simulations we would have had to have done to do all of them. So instead, we did machine learning. So I still had to do 100 simulations in order to train the machine learning model. And don't ask me about the machine learning bit, because I know nothing about that. My colleague in Waikato did that. But what we found was he picked out which runs we should do to train it, and then we did some other runs and then tested it against what we found in the CFD. And we found that the machine learning could identify where these turbulent structures were occurring quite well. First of all, we did 2 experiments. The first one was whether it could predict these turbulent structures, and we found that it could. And the second one was, could we predict whether they were happening in front of the dune or behind the dune? Because that's really what we wanted to know. And this was our second. This was location prediction of the turbulent structures. And it's color coded in terms of how well it predicted, etc. But I'll get to the sort of crux of what we discovered. So what our first experiment did was, can we identify when we're going to get these turbulent structures either behind or in front of the dune? And we discuss and what are the important parameters, variables that will predict this. And we found that wind orientation angle was the most important. The cases decreased significantly as the wind angle is orientated to shore normal, i.e. perpendicular to the dune. We found that dune height, we were less likely to get these turbulent structures at very low dunes or very high dunes. So very much the sort of 3 to 6 meter dune heights, we were more likely to get these. And then we had wind speed and dune slope were sort of equal pegging in terms of importantness. So more likely with steeper slopes, for example, more cases at higher velocities at larger, more longshore angles, for example. And we found that the crest width made very little difference. In experiment 2, this was, can we predict where these turbulent structures are going to occur? Front or back of the dune, stot or lee? And we found that actually, in this case, it was the crest shape that was really important. So for the stoss, and those are the really rare ones, the ones that happen at the beginning of the dune, the front of the dune. So they only happened when we had quite peaky crests. And then dune height was slightly important. Orientation angle was, again, a really key factor. So that's where machine learning was really useful because there's no way we could have done all of those simulations. And in fact, well, I could have done all those simulations, but I would in no way have been able to determine these pattern of behavior if we hadn't used machine learning in the way that we did. So I think that was a really interesting sort of exercise and really allowed us to sort of develop a bit of a conceptual model about how these turbulent structures happen and when they happen. Okay, so I'm finishing off now. Hopefully I'm not too out of time. To answer some of the big questions about the dune systems, I think as a modeler, we need definitely understanding of that physical context. We definitely need to get into the field, even if it's only once or twice, to really understand the connection of your model to what's going on in the field and how difficult the field is and how the wind behaves, how the dune behaves, how the vegetation behaves. And then understand your assumptions and your simplifications. You really need collaborators who can do that work for you, that you trust, understand what you need, and you can talk the same language. I've built up this relationship with my colleagues in geography over, a couple of decades, and that's been really important. And we need to, as I say, we need to go in the field, even if it's very uncomfortable or alien. We just hope that we pick a nice day. We want the wind to blow, but we want sunshine as well. We don't want that horrible rain stuff. And we need to understand how the data is measured and what the limitations of that are, but also what the power of that is, that we can get some really big sort of records of data, but sometimes that our data loggers can fail. And we think we've got a really good set of data and then we go to plug it in and it's all gone. So that's just the field. And in terms of data and the context, hopefully I've shown that it can motivate the creation of a new model. Just going out and observing and thinking, actually, we're not covering this in our CFD model. What can I do to make it better? It can prompt the adaptation of an existing model. So we can try and better understand some of those conceptual models that already exist. And obviously it can help with simplifications to the model. And it can validate or not some of the assumptions that we're making. So I just want to say thank you. Thank you to all my collaborators, and hopefully people have found that interesting. I did rattle through it, so sorry. But read the papers, that gives you more.
All right. Thank you, Sarah, for the talk.
That's
There are some
okay.
clapping on my screen. I hope everyone can see it. Okay, so we have a bit of time. Do you have any questions from the audience? You can put it in the chat or you can just unmute yourself.
Maybe a
Natalie.
hand up. Yeah.
Yep.
Thanks for the talk, Sarah. Very interesting. I
Okay.
was curious about, I mean, erosion and deposition. Are you, I mean, is the implicit assumption that erosion is always basically proportional to the shear stress on the bed? Is this?
Yeah, well, that's sort of the assumption we make because we don't model the sediment,
Yeah,
because that's quite difficult. Yeah, we sort of make that a little bit of that assumption. So we do look at that wall shear stress. Yeah,
yeah,
that's all we can do really.
yeah.
Yeah,
And what about the deposition? Then the deposition is a bit well,
it
deposition, if you
is.
don't model the transport, then would be harder to predict,
Yeah,
right?
we
Yeah,
it tends to be in those areas of very low flow. So we see from the field that it happens in the lee of the dunes, not
yeah,
surprisingly, those recirculation areas. So, we know that sand drops out either of saltation or suspension at a certain threshold velocity. So that's one of the things we can use. We can sort of look and see where the velocity is, below that threshold and make some assumptions then about that. And it does tend to be in those areas of recirculation and very low flow that we get depositions. So yeah, that
okay,
first work of Dux that I showed, that's he sort of matched up some of those areas of low flow with areas that where we saw, through surveys that were done, of where we got sand deposition. Yeah.
yeah. Thank you.
Can I maybe follow up on that one? Because I actually had a question with the shear rates as well. And I was just wondering so for example, in the blowout work that you were doing, if you're able to identify kind of like safe and concerning shear rates for that particular dune and whether that was influenced by things like moisture content in the dune or like the grain size distribution of the sand or if any of these types of aspects
Um,
were considered.
no, they weren't. Too difficult.
Yeah,
Yeah,
yeah.
I
I
didn't
thought it
even
might be.
mention that. No, I didn't even mention. Yeah, I mean that's the other thing about studying coastal dune systems is you get rain, you get moisture, yes, and of course you get different size sand grains. It's just so complex. No, we don't do any of that. It is relatively simple in terms of how we think about, our sediment transport. We try and match it up, and that's why we do the sort of catching the trapping of sediment to try and, sort of marry some of that up sometimes. But yeah, no, it's not as simple as that. Actually, one thing I
Yeah, I
didn't
didn't think it
mention
would
in
be.
my roughness, one of the sort of unexpectedly, we were doing field work in Stewart Island, and I came a little bit later, um, and my colleagues had already actually done the experiments because they had a good wind window, and they'd actually put a mast up on the beach, which I hadn't really thought about. I didn't really need, and we looked at the data from that, and interestingly, when we look at the relationship there between roughness of the beach against wind velocity, we find that it's the opposite to what we expect. So as the wind blew harder, the beach actually got rougher. And I think that's because the wind is blowing away all the fine dry stuff on the top and sort of uncovering some of the wetter, coarser stuff on the bottom. So actually that was a sort of really interesting result. I'm not sure how to use it yet. I can put it into my model, but it's yeah, that's just an illustration of yes, these things are complex. So yeah.
Yeah, yeah, complex and very interesting. I think Hubert has his hand up as well in the Zoom.
Sarah, thank you very much for your talk. It's great to see field work on CFD modeling together. That's not very
Thank
often
you.
we see this, so very well done. I have
Thank
a
you.
I have something a little bit more practical in terms of your application. In terms of
Mhm.
dune protection, it's very common to use porous fence or even porous fabrics that you lie on the sand to try to reduce the amount of erosion. Did you try
Mm.
to use some this type of protection with a porous fence or porous fabrics in your numerical modeling?
No, I haven't actually. That would be quite interesting to have a look at actually, sort of, and in some ways that would regulate some of the roughness that we have. We it would probably be a lot more measurable. No, we haven't thought of doing that actually, and that is a really interesting idea. I mean, sometimes we actually want the sediment to flow through, because that's a way of moving the sand around the beach. And we often hear about parts of beaches that get deprived of sand, and we want to move it around. So that was part of the work with the notches, was to try and can we sort of steer the sediment, the sand, into the places we might want it. So yeah, no, that's interesting. I hadn't thought of that, but that might be a really interesting little experiment to do. Thank you.
Thank you.
Sarah, may I jump in and ask a question? So I was wondering, how did you measure the roughness of the sand or of this vegetation under wind deformation?
So what you do is you do it via the velocity profile. So I haven't got it up here, but you find the velocity profile and you plot it in a certain way, and you get the Z0, the roughness height.
So it's basically from the log shift.
Yeah, basically. Yeah. So that's the only way. Sand is sort of, we just use a sort of known sand roughness height. But yeah, for the vegetation, we just do it like that. So we started off just using constant values for our vegetation, but again, being out in the field, we realized that actually, doesn't really cut it. It varies all the time. So yeah, and different vegetation has different ways in which it varies, whether it's tall marron grass, which can be up to 0.5 meter high, and bends quite a lot, to some of that low lying stuff that we saw on Summerlands. So yeah.
Yeah, thank you.
No worries.
Maybe just ask one more on the CFD side, so we just have a little bit of time left, if that's okay.
Absolutely.
You sort of, I guess, triggered my mind to it when you talked about the wind coming in and blowing like the faster wind having kind of an unexpected result. And I was just curious on the CFD side, how are you modeling that inflow profile, and is there much sensitivity to like the turbulent intensity or these types of things that you specify in your models?
We model, so we look, because we've got flow over water, basically before we get to the beach. So we have two simulations. I model the flow over a water with a roughness for the water, and then use that as the inlet for my beach. So yeah, we haven't tried different intensities. The beach actually is usually relatively long, so the fetch is quite long, so it tends to sort of stabilize that velocity profile. But we've tried it at different sort of free stream velocities, and we get similar sort of patterns. So yeah. But the trouble at the moment is that my model is quite, because of the field data, it's restricted to a really narrow range of velocity. So I've tried different velocities, and we do see it works with different velocities, but I'm sort of restricted because my model only works in this really narrow band of velocity at the moment. But yeah, hopefully my colleagues can get back out in the field or dig some other data up for me that I can expand out my model. That's the dream. So yeah.
Yeah, thanks for that.
Okay, I think we don't have more questions from the chat. All right, so maybe let's thank Sarah again, and we close the session.
Thank you for inviting me and for the question.
Thank you for the talk. Yeah.
Thanks.
See you all in Christchurch.
I hope so.
Thank you. Yeah. See you in Christchurch for
See
sure.
you. Yeah.
All right.
Thank you.
Bye. Bye, everyone.